Okay, so thank you very much, Themis. And I'm going to introduce you to the first part of the scientific agenda. So I'm Jackie, and this is Marilyn. We're the co-leads of this part of the hub. So it's based on AI-driven materials discovery and device design. So what you're going to see this morning is, on the one hand, showing you what our postdoctoral researchers have been doing in the hub. And we're then going to look at what the students associated with the hub have been working on, and some really nice work there as well. And then we've got examples of project collaborations with the wider network of the hub, and you'll also then see examples of what the April Hub Fund that may be helpful. And then we'll summarize. This is the core team, just so you can see who they are. They're mostly sat around the front row here, so you can pinpoint them later in the networking sessions. And we're all working on this theme. You'll see throughout the presentation this morning, we've got these kind of icons that are trying to show the value chain of the whole process, from materials design right through to device optimization. And we've tried to use icons to show you at each point in the research that we'll show you which point, in this value chain we're looking at any one instance. But I think it's nice to show that jigsaw to see how it all links up, because that's really essential if we're going to see translation of this research into the utility. So looking at the first part of that value chain on materials discovery, you're going to see work on materials design and prediction. And in particular, I wanted to flag the tools that relate to the expertise that we have very much in the core team, ranging from mathematical topology, density functional theory, generative AI, property prediction, and some modular framework work for making efficient materials discovery. So you're going to see examples of all of that. And then now moving to the downstream part of the value chain, we're going to hand over to Marilyn.
Thank you, Jackie. So this is Pillar 2 about Electron device design, and it's co-led with Bipin, who's sat at the back there. Our vision is an AI-driven optimization of device and process recipes for faster development, higher performance, and improved yield. So basically, we want to develop tools that would automatically give us the kind of devices and the performances we expect of them. And the tools we hope to develop are generative design models for device and process optimization, hybrid models with physics and machine learning for device modeling, and automated data extraction and analysis. So I think I hand this over now to Alexandros. Thank you.
Hello all. Our journey in materials exploration starts with characterizing and understanding structure. I'm Alexandros Keros, and we will be discussing about phases of matter and how we can transition between them. Of course, this is not a new idea in electronics. Phase transitions have been widely explored and exploited to, for example, fabricate silicon wafers and come up with novel non-volatile memory modules, for example. Let's simplify the problem, though. Imagine you have a set of particles in a box, and these particles interact under certain dynamics. They can attain different configurations. They can be in a liquid form, in a solid form, crystalline, polycrystalline, or something a bit more exotic. The space of all these configurations is the configuration space of the system we're studying. And what we want to do here is identify how we can transition between them by changing the parameters of the system. And the parameters can be temperature, can be the pH of the solution, can be the salinity of the solution, etc. In order to circumvent some of the downsides that classical approaches have into understanding phase structure, such as being widely biased towards order, in the sense of we can identify crystalline structures. If it's something a bit more exotic, we go meh. And having only a limited view of this very high-dimensional configuration space, I'm using tools from algebraic topology and topological data analysis. To describe structure, I use a tool called persistent homology, which is a multi-scale tool, and it's very robust against noise. And it gives you a descriptor that looks a bit weird, but it's super expressive into how the structure of the particles has been created. Furthermore, I use a tool called Mapper, which is again borrowed from topological data analysis, to summarize this very high-dimensional configuration space into a simple graph. But the cool thing about this graph is that it can summarize the dynamics of the system as well. Doing that, we get an atlas of the configuration space, and this is the configuration space of a system of colloidal nanoparticles that you might know is quite a complicated system. Each node on this graph is a cluster of configurations that are similarly structured, and the edges in this graph tells us how we can go between these clusters of similarly structured configurations. Traversing this graph means that we can traverse between phases and cross between phase transitions. Furthermore, the structure of this graph, these splitting points, the bifurcation points, tells us a lot about the dynamics of the system. Because when these occur, that means that phase transitions occur. So we have a visual cue onto when phase transitions happen. Now, for each point of this graph, we also know the parameters that led us there. So we can do inverse design in the sense of like, we have an exact recipe of how we can traverse this graph and go between different configurations. To summarize, I'm using a quite noise-robust and data-centric tool that is multi-scale because of persistent homology, and it's theoretically backed by algebraic topology and differential geometry. What I have to do next is see how material properties manifest on this complex configuration space and the simplified view that we get. Ben, who follows me after this talk, will tell us a bit more about how we can predict properties of materials. But before that, I'm open to a few of your questions. Thank you. Thanks for the questions. So why is my structural descriptor noise robust? Actually, persistent homology is theoretically robust because there is a theorem, it's called the stability theorem of persistent homology, that essentially tells you that if you move the particles a little bit, your metric, which is persistent homology, shouldn't change a lot. But if you get significant changes in the structure of the particles, this means that the metric should change accordingly. So we have a theoretical backing of why this is robust, which might not be the case for other metrics that are classically used. Furthermore, I think yeah, okay, yeah. So that's it. Any other questions?
To what extent have you been able to validate this approach so far? Is that work still to come?
So we've extensively used molecular dynamic simulations with a model called DLVO model for the colloidal nanoparticles, which has been experimentally verified to coincide well with observations through AFM microscopy, for example. Now, the next step to verify it is to actually give a recipe to an experimentalist and let them verify it in the lab, which is the next step that we want to do. Thank you. I'm going to give the podium to Ben, who will tell us a bit more about phase transition, predicting properties.
Great, thank you very much, Alex. So today I'm going to talk to you a little bit about generative AI is dreaming up millions of new materials, and actually, are there any good? So the motivation behind this is, in the recent years, several significantly, very, very big companies have been producing these generative AI models based on generative adversarial networks or diffusion models to come up with new inorganic materials. It's kind of building on the AlphaFold project that was pioneered by Google DeepMind team, and I think quite a few other groups are kind of cotton onto this. Is this something that we can look into for inorganic materials? You can see this is just a small sort of snapshot of all of the different approaches that have been taken. I don't think any of these work particularly well. But the ones I really want to concentrate on today, and you'll see with some of the internship projects, are these models from Microsoft and from the Google DeepMind team. But it begs the question, AI is dreaming up millions of new materials. Are they any good? So with my background as a nanofabrication engineer, I'm really interested in two types of devices, and those are thin film transistors and memristors. So for the purposes of this talk, I'm just going to, I won't touch too much on the memristor device itself, only to say that the switching layer, the resistive switching layer right in the middle there, is very key to the operation. There's then two metal electrodes above and below. And what we're really interested in is understanding what are the kind of properties of this resistive switching layer that are really key to how it performs. The first one is the stability, so that's called the energy above hull. Is the material stable? Then we will be interested in the band gap, some of the electron mobility, the carrier transport properties, the dielectric constant, and the vacancy mobility as well. So this kind of forms what we call an inverted pyramid structure, where we might take, I don't know, 1 million new materials at the very top and filter them down based on these structural feature relations. For the purposes of this short discussion, I'm going to talk about just the band gap here. And what we want to do is produce a surrogate model for these, so like really lightweight, very fast calculating model that kind of bypasses the very computationally expensive DFT calculations. And so to do this, we leverage a pretty sort of standard machine learning approach called a gradient boosted decision tree. Essentially, it's an ensemble of decision trees built sequentially, with each new decision tree fitting the residuals of the previous one. And we optimize via gradient descent on a loss function at this point. The final prediction is just a weighted sum of all of the trees. This is quite robust for this kind of project, this kind of problem, because they're high accuracy, they handle non-linearities well. They are also fully explainable, so each time you make a new leaf in this tree, the decision is fully interpretable by a human. The cons of this particular approach are they're quite sensitive to the hyperparameter tuning, including the learning rate and the number of leaves and trees that we fit. So that leads to a risk of overfitting. So the way we train these models is we actually used a corpus of literature extracted experimental band gap measurements, which is really interesting because it's kind of farming the data from the literature corpus. So all of these are experimental values, which I think is kind of a key novelty here. So what we need to do is we need to turn these generative AI generated materials into a set of feature descriptors. In this case, we have about 600 quite sparse features, and by sparse I mean there's lots of zeros and lots of sort of missing information. So by a process of gradient boosted feature selection and recursive feature elimination, we can actually reduce all of these 600 sparse features to just 70 key relevant features. And again, these are all chemical descriptors, so they're fully interpretable, combating the black box nature of machine learning using neural networks. So how do they perform? It's a good question. This is, if you look just at the specific RMS values and the accuracy scores, not particularly great, but I think the key thing to remember here is that each of these points is a single scientific publication, which means there's going to be variance in the measurement technique, variance in how these values are reported. And so I think it's still very interesting kind of result. And we're sort of combating the overfitting by a nice evenly distributed or normal distribution around the residual error there. So yeah, very promising result. And so we're trying to now look into not just using these in the forward design process, the inverted pyramid process, but also trying to look at, can we use these generative models as part of an inverse design problem? So actually conditioning those initial generator materials on these properties by leveraging these lightweight surrogate models at each of these stages. So the next steps for this are to collect more data for not just the band gap, but also some of the other properties of interest. And by doing that, we can use these adapter modules, which Jamie is going to talk about a little bit in his presentation shortly, to condition that generation process. So it's really we're looking towards an actual designing a material based on the properties that we're interested in. Okay, and so that's me. Thank you very much for your time, and open to some questions. Okay, cool. So can we expand this to beyond semiconductors? Absolutely. This particular framework is, if you've got good data from the start, you can adapt it to whatever properties are of interest. Does the training on experimental data incorporate information of the experimental errors? Very good question. So in the auto-extracted experimental values, we typically aren't reporting the measurement error in the first instance. So in this case, it's only incorporating it as far as the initial data that you're training those surrogate models on. In terms of some of the state-of-the-art generative models, I think that's up for debate. I think that's still a very new field. A lot of these models come out just in the last year. So the field is kind of trying to get to grips with this. Is this something that we can actually practically implement? Do we have time for one more question? Property prediction beyond bandgap. Absolutely. As part of this project, I also was looking at the dielectric constant. So we had, from the literature corpus, these auto-extracted values. So we could fit models in that, which I'm happy to talk about more over my poster later. Thank you very much for your time. And I'm handing over to Shashank, who's going to talk about integrating some of these properties of materials into a device context. Thank you very much.
Hello all. So till now, just now Ben was talking about property prediction of materials. Now I'll show you how can we integrate those AI tools into prediction of performance of devices. So to model a device, it's not only about materials, but about other things as well. So for making a model, we need to consider in 3 parameters. So that the parameters like material properties, the design parameters, and the operating conditions. So let's take a case study of a triboelectric nanogenerator. So triboelectric nanogenerator is a device that converts mechanical energy into electrical energy, and it is widely used for energy harvesting from sources like rain, wind, and ocean waves. And in a way, we are trying to make devices that can be helpful to AI, which can give energy to data centers and all. So it works on a very simple mechanism of contact electrification. So what happens is, once there's a pressure on this device, there's some charges developed at the interface, and we type in those charges in some capacitors. So there's generation of some kind of output voltage or current in that case. So what I wanted to do was, I wanted to make a model that can predict the output voltage and current with given sets of parameters. So the first sets of parameters that we need to consider is the material properties. So material properties like band gap, homology gap of the active layers, and the resistivity of the electrodes matters a lot. Then you have the design parameters. So design parameters could be the separation distance between the layers, the thickness of each layer, the contact area, and the form factor, like whether it's a thin film material or is it a electrospun material, and all those things. So we need to consider in all those factors to make this model. And lastly, the operating conditions. It constitutes of factors like temperature, frequency, and load resistance. So my aim was to make a unified model that can capture every key parameter to make an accurate model. So how did I do that? So I took a typical data-driven approach where initially I curated a data set of experimental data. So what I did was I manually extracted data from research articles, and I tabulated all those parameters related to Ting, and I had total around 400 data points. I had some sparsity in this data, which means not all the research articles mentioned all the parameters that I needed. So in spite of this sparsity, I will show you the model was quite good. Then I featurized my data. It means I converted my data into machine-readable format. And herein, I tried to leverage AI models that just Ben showed. So I used some AI models for polymer, known as polymer genome, for getting homo-lumo gap values. And for band gap, I used some open source material database. And this, after featurization, I had like 39 features in my data. And then I made a model using gradient boosting algorithms like XGBoost and LightGBM. These models were chosen because they can handle sparsity natively. And finally, I validated my models using 5-fold CV and also incorporated uncertainty quantification techniques in my model. And here are the results. So you can see these are the parity plots for both these models. And on x-axis, you have the experimental values, and on y-axis, you have the predicted values. And the more the dot are near the diagonal, the higher the accuracy. And I got achieved around 91% accuracy in these models. And both these models showed identical performance, which means that my data set is non-biased towards any particular model. So the key takeaways from this exercise were that sparsity is not always an issue, and we can actually predict performance of such devices even from small sparse data sets. And moving forward, I would like to create some inverse design models where we can get an accurate device structure for a given output voltage or current values. Thank you. Okay, so how does the model compare with current physics-based or empirical models? So actually, the current models that are used, like COMSOL or all those things, those don't consider factors like surface roughness or humidity and all, which are very crucial for the functioning of these tribolectric nanogenerators. And I am trying to incorporate those factors as well in my model, so that's why I think this approach is better compared to physics-based models. Any limitations of a model? Yeah, so currently the model is a bit interpolative. I have not tried extrapolative things, so I'll try to see how my model works beyond the domain of the dataset that I have. And it works only for the vertical separation mode of tribolectric generator, but I'll see if I change the mode or the type of thing, will it work? So yeah, that's all. And with this, if there's no more questions, I will try to call Lai on stage. He will show you how can we create our own data set through automated characterization. Thank you.
Hi. So today I will give a short introduction to our automated Memristor research system. So Memristor is a kind of device that's history dependent, which meaning its behavior is shaped by its past states. So we should have some recording of the device's entire life. Our goal is to combine the prior knowledge with the AI-based tools to better understand the behavior of the device. We created some our own data pipelines to collecting all the data from the material and process, electrical characterization, and the extracted features and derived models. So for the first stage, we are collecting all the steps recipes, fabrication recipes, including ALDs, filtering, all those etc. And so each wafer will have a fabrication record. And then we put into robotic probe controls with ARC1 measurement board. So this can automatically and consistently collecting all the electrical data points. Then we're utilizing those collected data points to do some feature extraction, such as to discover the behavior of the forming, volatility, and switching of the memory systems, and then derive them to the models. All those informations will be automatically and simultaneously collecting into a single prevalence-aware database with some structure like this. So far, we have collecting about 98,000 of the experiment, and it's already continuously collecting in the lab, 5 GB of data. This builds the foundations of the discovery for the crossing stages analysis. I also use the collected data to do some forming behavior discoveries. So first, I select the data and do some of the standardization of it. Then I put it into an autoencoder to reduce the dimensionality of the recorded data. Then put into some clusters because I don't want to manually label all the data and put it into the, so I'm using the clusters. It's an unsupervised method. Then it's like I manually label a few of them to say how good the data, the model's prediction, and it shows interpretable and very high accuracy labels to explaining what's the behavior in different classifications. And this built in a growing knowledge base for the understanding of how the automated collecting data and how we're utilizing the AI tools to understand the memory resistors behavior and opening the door for more holistic memory resistors research. And that's it. Start with first question. Does the pipeline generate to other devices? It's quite a good question. For now, we are building the pipeline for the memory resistors, but in the future, we could build some pipeline for transistors or other kind of neuromorphic devices, just changing the storing format in the fabrication part. How time consumed is automated the pipeline? This really depends on the characterization protocol we made. For example, if we want to measure the device behavior based on all factors of the behaviors, for every device, we will take a long time, such as if we want to measure the retention of the Memristor, then it will take a few hours to stay here and to measure it to see how the behavior looks like. Yeah, this really depends on what kind of thing we want to measure. Yeah, so we pass it to the Shangzhou to do the data extractions and how we combine all the data source to do the optimization of the device. Yeah.
Thank you, Lai. So today, I'm going to show that how we accelerate the automated system that is AI-driven and that is designed for the device, especially how to accelerate through the data logged in the literature of the scientific manner. So how we do that and what is the reason that we are doing that? So there's a whole pipeline where we start with the data. That's, there could be a different ways to get the data. Let's say from the industrial experiments, also like labs, they have the experimental data or the simulation data. But there is another way to get the data extracted from the literature itself. So for instance, we start with the initial data and then, so we start with the initial data which we can get from the different sources. In our case, we are extracting data from the literature. That data is fed to the ML model where it will be training and validating the data through the ML model. And that will calibrate according to the physics behind that one. That will drive to the optimizer, which will provide us the optimized design. That will again put that one to the simulation, so that simulation will validate our results from there. And that validation and simulation will tell us that whether we need to update that model, retrain the model, that will also be possible then. And later on, we will get the optimized parameters which can tell us this is the device we can achieve this particular performance. For instance, we have the simulation, we have the structure of the device. It's a FinFET. So let's say we would like to get that FinFET optimized way, and we can optimize that one in, let's say, high performance or the low power or low area. And that behavior can be taken from the literature itself. So that's the reason that why we are extracting the data, because in the starting of the pipeline, it is a fuel for this engine, this whole system, that will accelerate the device design. So this is the reason of we are having that data extraction pipeline. In that data extraction pipeline, we will automatically search the literature, a specific paper. You can feed that PDF or XML or any kind of source to the system. And that will apply the extraction method, just like optical character recognition and NER as well, with the help of LLM integration, validation, and the selection of the specific type of the data. And then we can extract the parameters, let's say physical parameter, as I showed in the previous slide, that physical structure of the device, we can extract those parameters, also the behavioral parameters, and we can also extract the derived parameter through that one. And so after that, we will standardize that data so that it can be utilized for the ML modeling. And from there, we can have the automated ML pipeline, which can extract the data, which can provide the data to the ML model, and as well as we will get the optimal design. How this pipeline works exactly? So let's look at that. So we search literature automatically. We take all figures from that particular PDF. We store them in a repository, and from that repository, the system will automatically take that particular image. And because it is an image, we will put that image in a framework or the canvas. In that canvas, we can take the different element of this plot. So for instance, these are the axis values, and these are axis elements, and the curve elements. So we separate them. So first, let's say we can extract the plot elements, axis values, axis labels, that's one. And we can have the axis pixel value as well as the plot values, the actual values. And another engine which is running parallelly, that will tell us how many curves are there, what are the data points of those curves, and then give us the XY axis pixel values from there. We combine the pixel value as well as the data value and then map them together so that we can have the exact value for the particular pixel. And we use the common centroid condition for that so that we can apply a particular value for those pixels. And after that, we will get the results in the form of CSV. We can plot and verify by overlaying together with the input image and the output image. And then you will get the data. So you can have multiple plots, and then you supply to this system, and you will get the multiple data set. And then you can process that data set and create that data set for the ML modeling to validate, to train, and retain the data. So with the early results, we can see that this is showing very good results because we have seen the previous slide where the input was very close to the output image. So that will save the time because whenever we are going to, for instance, Shashank was trying to get the data from the literature. He was getting the data or extracting the data manually from one plot to another plot and from the bar graphs. So it might take 15 minutes, 20 minutes for each graph. And before that, you have to learn how that tool works. And that learning curve as well as the data extraction for each curve manually takes time. So let's think about that if every researchers go do that one. So it saves time, and it is 5 to 7 times time-saving environment here. And with the reliability. Also, it's not the perfect system, obviously, because the tools or engine I showed, they are also ML-based, so we need more data to train those models as well as. So that's not perfect, but still we have the luxury that we can extract the data from some plots. Let's say out of 10 plots, we can have 2 or 3 or 5 plots. It depends on the complexity of the plot. So this is all about that we are creating a data set possibility that can be extracted through the literature. Thank you. So I will take some questions. Yeah, sorry. Can this be used to gain additional insights from historical? Yes, it is. Just because, let's say, if literature is very old and the plot has many things which we cannot see, so we can have from the literature itself, let's say from the PDF and the document, we can pass the information to the text, to the tables, and also the plots, so that we can combine those values and the metadata and extract those values. So yes, it is very good to extract the data, and it can be possible. How do you validate the accuracy of the extracted data points? Yeah, that's a very good question. So we validate with the overlaying and then go with the LLM as well as the OCR engines, and then check the values manually, and also with the R-square and the RMSE validation. So that's way we can validate the data set, which is good or not. And then if it is not, then we can also go for, like it's through the system, the data set is not good, and we have to go for the manual extraction or other ways to extract the data. What criteria will you apply to screen the relevant paper and articles? So criteria is, let's say for FinFET, so we go for the FinFET simulation or experiment. So we apply these key terms, and then we download those articles specifically for that one. So it's a manual process, obviously, because if you are searching some articles and that doesn't have the data set plot which you require, then you have to understand that, okay, this is the thing we have to get from the data extraction. So yes, we can do that and we can apply that, and this way we can get the relevant data from there. So manual intervention is required there. Yeah.
Do you consider temporal-related inversion property of FinFET?
Yes, yes. So as I was talking about that, we have to extract all the data. This is just a plot data, but there is a data in terms of text and the tables as well. So we'll extract all the metadata there, and we combine all data together so that we can extract secondary properties as well. So for that one, yes, we will extract the data also. You're welcome. Oh, thank you. So now let's move to EMOS. That's an electronics material operating system, which will be presented by the Atish. So welcome, Atish. Thank you.
Okay. Thank you, Chandraban. Well, state-of-the-art AI-based materials discovery is very good at giving us some candidate materials for certain desired properties that we're looking for. But I think as an electronic engineer, if we are involved in device design, we want something more. We don't want just the materials that can satisfy desired property conditions that we're looking for, but we rather want a materials that's applicable to the device or the application that we're working for. To bridge this gap between the AI materials discovery and the demands from electronic device design, we proposed this framework called Electronics Materials Operating System, EMOS in short. This is an open source, community-driven framework. We are publishing it as a web application for now. And it's an interoperable framework which gives access to electronic engineers from the building blocks of AI-based material discovery, like databases, generators, predictors. There are a huge number of these resources available, but they are fragmented at the moment. This framework will give access to them in just one go. Plus, it will also give engineers to create their own custom pipelines called features, which will be based on each application. So there is a freedom there. The way we are trying to build this framework is in 3 phases. We've just finished the first phase, so the design is ready. The web application is available on April's website. I will give you a small demo at the end of this presentation. We are right now just entering phase 2, where we are trying to actually fill in all these information units to the application so the users will have access to them. The idea is very simple. It's an open source GitHub repository, so anyone should be able to, whoever have access to the repository will be able to make their contributions. And the backend is designed in Python, so it's very easier for anyone with Python experience that they can contribute to it. Let me just go and see if I can share this on our website. Okay, it's available here. You can go to the April's website, and under research, you can find EMOS app. That's how you can access it. The idea is like this. You have certain information units available on the left-hand side. You can choose the features, which are also customizable. So let's look at, for example, this one over here. It takes a little bit time to load the, let me see if it's loading correctly. It will take some time. But the idea is that for each feature, you have access to all these things that you can click and select. For example, you can choose materials like, databases like Materials Project, or a generator for MatterGen, which is being used inside the feature, the device design feature that one would go for. This method of just picking and choosing databases is very novel to this framework. Because if you have to do it for ourselves, and we've learned it through our experience with our interns, Jamie is right here, he will talk about his project. It takes months to do this. With this framework, this can be done with just a simple click. It will be available with, now you can see here. So for example, you can see which databases it's using. So I can remove, let's say, materials projects and just stick to ICSD for this feature. And you can only say ICSD instead of materials project. So it's making the materials discovery this simple and available on the fingertips of electronic engineers. That's what we're trying to achieve with EMOS. And I'm looking for other researchers who would be interested. So I have a demo and a poster. So feel free to get in touch, and we can discuss more. I can take questions now. Thank you. Can we train our AI models on EMOS? At the moment, the backend is also it's a server online, and it's only CPU-based. But in future, we will have a GPU-based server. So once that's there, you can train AI models on the EMOS. But for now, you can just upload, you can use the available predictors and generators that are already given on the server. That's the plan. And the next one is, how do you plan to validate the features? So if you remember, there are 3 phases. Each phase relates to one role. So the first phase was the role of a designer and an admin. So admin makes sure that the features or any information units that's being uploaded to the system meet certain criteria. We've defined certain criteria as whether it's accessible, whether it's the description is good enough, because we are also providing user documentation with the website, if that is clear enough. As far as validation is concerned, the scientific results, it's a bit tricky for EMOS because each feature has its own custom pipeline. So there is no standard benchmarking that one could go for. But we have guidelines for accepting contributions that will be used as a validation here. So I think if there are no any other questions, we can move forward to the next session, which is being hosted by Shashank and Chandraban for our interns. Can you maybe come forward? Thank you.
Thank you, sir. Thank you, Atish. So now we are moving towards second module of this session. And this is about showcasing our Google DeepMind research-ready internships projects. There we also go through the same structure like material exploration, property prediction of the materials, and the device optimization as well. So our research interns have worked on very rigorously on that. So there are 6 interns which are related to this field, where Jamie, Isa, Jofa, and Mohanad will be presenting today. And we also have 2 interns, which we are not having here. So they will not be presenting today. But the Abdul Halim and Abu Salim, he has also worked with us. And Masimula Tamburski also worked with us for the pin networks and optimizations. So without few further delay, I would like to call Jamie to present his project.
Hi. You've likely seen how generative AI can be used to, say, generate a new image or a new video from scratch. I want you to take that exact same process and apply it to the physical world of materials. So not asking an AI to generate an image, but to generate an entirely new novel material with targeted properties in mind. So my internship mainly focused on using MatterGen, which is a generative diffusion model, that has been created by Microsoft, which is essentially trained on 600,000 materials. And it starts with the most stable form of this material and breaks it down iteratively until it's a random amount of materials. And then you can then reverse this process back to then generate new novel materials. And it does this based on the atoms, the coordinates, and the lattice of the materials. So we were looking at key electronic properties using this type of framework, mainly the chiral mobility of the material, and also high-K gate dielectrics, which is work that Halim worked on. So essentially, the architecture has this pre-trained model and then adapter modules like Ben had mentioned that you can fine-tune on. So essentially, we used two different data sets. One, the MATHub 3D for electronic transport properties, and also the materials project for the high-K gate dielectrics. And essentially, we fine-tuned these adapter modules to then be inserted into this pre-trained model so that we could generate new novel materials with these specific characteristics in mind. So essentially, fine-tuning and creating these generated materials with these specific properties, chiral mobility having an impact in potentially faster and more power-efficient chips, and high-K gate dielectrics for smaller and more reliable transistors. We also are exploring different frameworks for AI synthesizability tools so that we can also determine the potential of translating these generated materials into the physical world. So, thank you.
Thank you, Jamie. Now I will call the Joseph. Please have a podium. Thank you.
Okay. Okay, so everyone in this room uses AI, but have we actually stopped and asked ourselves how trustworthy these models actually are? Because machine learning is increasingly popular in materials design, and because of the black box nature of AI, these models lack interpretability and they don't really quantify the uncertainty. So, hello, my name is Zofia, and today I'm going to present my internship work on improving trust and reliability of machine learning models used in material design. So, how do we do that? We followed 6 key steps: data collection, featureization, feature selection, model training, uncertainty quantification, and validation. However, the models I used were not just normal models, because instead of just giving us predictions, they were also giving us confidence intervals, so basically telling us how certain we are about our future predictions. As we can see, the results were pretty good. You saw during the previous presentations as well that the R-squared scores were pretty good, the errors as well. However, if we actually plot the uncertainties as well, we can see that each of our predictions comes with a risk, and our job was to quantify this risk. But, well, why is it important? What is the impact of this study? So, through uncertainty quantification, we can improve accuracy and interpretability of our machine learning models. Through that, we can improve trust and reliability. And that leads to safer, more explainable materials discovery. So in the future, we plan to integrate the uncertainty quantification techniques into the current materials discovery pipelines, because with uncertainty quantification, we don't just want to make predictions, but we want to make predictions that we can trust more. And if you want to know more about what models are used, what techniques are used, and have a look at the more specific results, please come and talk to me during my poster session. Thank you.
Thank you, Josa. Our next speaker is Isa Sadiq. He would be talking about the machine learning approaches for the prediction thermal behavior. Welcome.
Hi, everyone.
So my project was on predicting thermal properties of semiconductors. And just for a bit of background, I want to start with something you're probably familiar with. In Moore's law, obviously there's been massive sustained progress over the last 30 years in computer processors, and in large part due to engineers managing to fit more and more transistors on a smaller scale. And so with this, the processors consume more power in a smaller area, or there's more power going into smaller areas of processors. Obviously, it leads to large heat buildup. And so what's happened, we're reaching a kind of a regime in which temperature dissipation is becoming a major bottleneck in chip design. And so this puts quite a lot of pressure on material scientists to find new materials which can help to dissipate that heat quicker. So in effect, finding materials with high conductivity, along with all of the electronic properties that we're interested in for chip design. And so the main challenge with this is that it's actually surprisingly difficult to predict conductivity because of you have to model the vibrations of atoms, which is dictated by electron interactions. So you have to do very expensive, essentially quantum simulations. And so this was kind of just an accepted compromise of cost and reliable or efficiency of those predictions up until the last 3 years or so, when machine learning has been introduced to make those same kind of forced predictions. And so my project was on integrating those machine learning models, the foundation models, which are publicly available, into a pipeline for making a conductivity property prediction using conventional simulations in solid state physics. And I'd say the main finding I found was that the accuracy of those first stages of the very simple steps of that pipeline don't necessarily correspond with the final accuracy, so that you can rank models differently depending on how complex you actually make, where in the complexity chain you make your validation. And so if you'd like more information or more details on the methods or the results, please come check out my poster. And yeah, I just wanted to highlight how this area of applying machine learning models in physics-based simulations is really exciting, and it's a very active area of research. Thank you.
Thank you, Isa. That was a great presentation. Our next presentation is a little different because this project was in collaboration with the industrial partner STMicroelectronics. So I'm pleased to invite Bruce Ray. He is an end-to-end product development manager at STMicroelectronics, and he will be setting up the context of the industrial perspective, that how this problem has been emerged and how the Mohanad has worked on this SPAD devices. And so please, over to you. Thank you.
So thank you for the introduction. So as has been introduced, my name is Bruce Ray from STMicroelectronics, and we set this challenge at a previous April event. It was actually set by one of my colleagues, Isabel Nicholson, who is a TCAD engineer within the imaging division of ST based in Edinburgh. Now, I've jumped into Mohanad's slides, so I'm not going to steal his material. Yeah, so basically the challenge was about improving the calibration of our TCAD simulations, specifically for single photon avalanche diodes. So these are quite unique photodiodes with unique properties, working beyond the reverse bias breakdown voltage. And they are very, very sensitive to a number of parameters, both in terms of the layout and the process used to manufacture them. So it's essential to have accurate TCAD in order to predict the behavior of these devices. And in addition to that, we're an industry player, and we're trying to implement these in very expensive advanced CMOS technology nodes. Our latest SPADs are implemented in 3D wafer stacking technologies. And therefore, it's an extremely expensive process. So in terms of time to market, the size of DOEs that we are doing to predict or to establish the design of choice, it's essential that we can down select and use TCAD predictably to accurately downsize that DOE and select the SPADs that we want to industrialize. So we asked the April Hub to look at how we can better calibrate our TCAD. So we do the designs, we have the simulation results, we take some of those to characterization, or we implement those in silicon. We have the characterization data, we have the simulation data. Very often there are offsets in the predicted versus measured. So using AI to learn those offsets, to correct for those offsets and improve the calibration of future simulation, which is clearly essential to improve the efficiency of that development loop. So with that, I'll hand over to Mohanad to give a little bit more detail and to share the results of his work.
Thank you, Bruce. Thank you, everyone. So, as you can see from there, that's a SPAD device. That green region is where we're trying to simulate. So, this region is where the photons avalanche, which we're trying to simulate and try to find the discrepancies. This is a SPAD device, and this was uncalibrated TCAD and measured versus measured data. So LiDAR systems can be used for many users. This one is from Edinburgh. They can be used in UAVs, reconnaissance, and many other useful things. So ST thankfully provide us with the TCAD simulation data, experimental characterization data. My main task was to try to do the pre-processing, train my residual neural network, and try to generate the calibrated prediction. So we went for a ResNet method, because this would allow us to just focus on the error. So if the simulation was very accurate, we will get like just the residual neural network would give 0. But if there is a discrepancy, this would where our work will take place. So it used something called skip connection. This would allow us to compare the simulation data with the characterization data and see the discrepancies. This is very efficient, so we don't need to go through the whole physics model just to replace it overall. So as you can see from there, we get very relatively accurate results. The R is the coefficient of determination. We got 0.87%. So a 0 would mean that our model is just guessing. There is nothing accurate at all. And a 1, it would mean it's very accurate, which is very difficult to reach. So we got a 0.87%. It's like 87%, which is quite accurate. However, our main aim is, as you can see, there's still some scattering there, which trying to narrow it down. So in the future, we're trying to implement a physics-informed neural network design, which might allow us to narrow that gap further and try to enhance our design. Future work might also try to develop a surrogate model where we can replace that whole process with something more quicker for the engineers to accelerate the SPAD design. Thank you very much.
So with this, we'd like to take questions for our interns. Okay, so we have some questions. So first question is for Bruce. How is STElectronics planning to use this, and what's next?
Yeah, I can shout. Can you hear me okay? Yeah, it's working now. Yeah, good question. So clearly we're focusing at the moment on the SPAD device. This is very pertinent in the Edinburgh office where we have a lot of focus on that device. I don't see any reason if we prove successful in this area. This is a bit of a showcase of what can be done, trying to link the TCAD to or improve the calibration of TCAD, which is applicable across all device development. So yeah, I would like to see us use this as a bit of a demonstrator and a pathfinder, and then showcase it to the rest of the company and how it can be implemented even beyond imaging, beyond photodiodes.
Thank you. Next question is for Isa. How did you benchmark your predictions, and what is needed for this?
Yeah, so that's a really good question. And so we used DFT calculations as a reference for all of those predictions made at each stage of the simulation. So that's like the force calculations and then first order force calculations, which are dependent on derivatives, and then second order force constants, which is dependent on the second order derivatives. And then along with the final conductivity value. And so, yeah, we specifically chose the material system to be silicon carbide, which is quite well studied and a quite well studied polymorph of that, because there's available DFT data for that. But it does kind of raise questions on when you want to model more interesting systems for which there might not be DFT data available, such as larger systems, which are unfeasible to do with DFT. Which I think that's a problem that needs to be approached when we start using these machine learning models for like really frontier level science, which is kind of their purpose. So thank you.
Thank you. Next question is again for Bruce, and the question is, how did you protect the IP of STMicroelectronics?
Yeah, it's another great question, because it was actually a hurdle that we had to overcome before the project could ever actually kick off. First, before that, I think that it's a hurdle that all of these type of projects or developments have to overcome. A company like ST being vertically integrated, we sit on a huge amount of data right from the process, the fundamentals of the process, right through to the product. So we're quite unique in that we sit on that data, and we can if we can protect the intellectual property, we can make it available. Other companies, fabless companies, they don't. So there is this interesting thing about open access to such data. But specifically for this project, basically it was a model coming from academia. It was data coming from industry. The data was being held and owned by ST. The trained model, trained on ST data, was unique to this project and owned by ST. But then the model untrained remains the property of the university and can be trained again elsewhere. So that's how we overcame it for this specific project.
Thank you. Now, I'll take a non-technical question first. So we have a question for the interns, and how was the experience during the internship? So could you like to comment on this? Any one of you? Jimmy?
Yeah, of course. I mean, the internship experience for me was very transformative overall. I just completed my bachelor's degree in computer science, so I had limited research experience, and I really enjoyed the process of my dissertation, my final year project. So being able to be part of a research internship like this and working on such cutting-edge research and the different types of links that the April AI Hub has, especially for even events like this, has been a very transformative and impactful experience in which I want to continue.
Yeah, sure.
So I come from an aerospace background, and this internship just offered me a total new perspective of what can be added to an aerospace field. In normal UAV design, we reached like probably stagnation point where there's nothing more can be added. But when it comes to electronics, there's a lot of creativity in this field. So it can take the UAVs to a different level when it comes to reconnaissance or LiDAR systems. So it was an eye-opener for me. We had a great time in Edinburgh, enjoyed the weather and the events, and looking forward to continue this further. Thanks for all the people who give us that chance. Thank you.
Joshua, would you like to add anything on that? Joshua, would you like to add?
Me?
Yeah.
For me, the experience was just amazing. I didn't really know if I want to go into academia or industry before I did the internship. Now, after the internship, I know that like being a researcher is something that I really, really enjoy. So, yeah, it kind of made me certain that I want to do a PhD and pursue a career in research.
Thank you. So in the interest of time, we'll call this off. We'll take this question offline, and we'll post these answers through our podcast and all. So please be updated with our website and all. And before handing to next module, I would like to thank Royal Academy of Engineering again for providing us the support to handle all these internship projects, and Google DeepMind and Edge Foundation. So thank you. Next.
Great, cool. So we're getting to the third module of this session. And so we're going to look at some of the projects that April funds through the seed funding program that we operate. Just to give a quick overview of the seed funding map for this specific session, each of the other sessions will also have their own seed funding that's kind of aligned to that kind of research. But based on the things that you've seen already in this session, we've got a few very interesting projects to highlight. And I'll also invite a few of the seed funding recipients to come and give them an overview of the research that they're conducting. So we'll start up in the north. We've got Professor Philip King at the University of St Andrews, who's going to be working with us on self-driving thin film synthesis of 2D materials. They've got an excellent molecular beam epitaxy facility there, and so we're going to be looking at some in situ measurements. We've got the group of Professor Mark Sorrell, who are looking at AI-driven inverse design for enhanced photonics. So I think it's important to emphasize, even though the April Hub is, from the outset, focused on electronics design, some of the lessons that we learn in this field can be applicable to other related fields, such as photonics. So we'll hear a little bit about that, I think, from Natale. We've got the group of Professor Bo Liu, who are looking at AI-enhanced reliability optimization of SRAM cells under process-induced variability. We'll hear from Ankit about that. We're going back across to the East Coast. We've got in Heriot-Watt University, Professor George Stelios, who are looking at adaptive machine-learned guided electrospinning system for smart nanoyarn manufacturing. I think it's pretty applicable to the work on the tribone electric nanogenerators that Shashank was talking about. Then we have to go quite a long way south to the group of Dr. James Bell in Cardiff, looking at robust artificial neural network device modeling for high-frequency nonlinear devices, or RAN. And then we go to the University of Southampton, where we've got representation from Dr. Naima Abdelazim, who's going to talk about some of her research. The group of Dr. Yassir Nouri, and the group of Dr. Ben Mills. So as I said, these are the seed projects that have been funded that are related most to this session, and all the other sessions will include the other projects as well. So without further ado, I'd love to welcome Dr. Naima Abdelazim from the University of Southampton to the stage to talk about the learning and predicting of aging properties of quantum dot security identifiers. Thank you.
Okay, so today I'm talking about part of my research, which is related to counterfeit. So, counterfeit is a big problem across, not just the UK, across all the countries, and I'm trying to actually create a quantum ID for fighting the counterfeiting. So, I use nanomaterials to actually create a quantum anti-counterfeit tag. This should be 100% secure and globally scalable, and we can use smartphones to read it. So it's based on a physical unclonable function. So in a very simple way, actually, we have an object here. Okay, we have an object. Actually, we can just sending some challenges by our phone, and we will get a response. The response transmit to the server, and then validate the response by the server. So this buff system actually based on challenges responses pair. So it is a mathematical function that is derived from behavior of the complex physical object. So the challenge response pair actually is a buff system, which is, as I said, one of the oldest form of authorization. Is based on a challenge and unique response and mechanism to match challenge and response. There's a lot of different applications based on a buff system, which is microchip, tamper-proofing, authorization, and true number generation, and so on. So in my research, I use low-dimension materials. So as I said, because it's based on a randomness, so we're looking to have a randomness response. So we have two different types of materials here. We use 2D materials. As you can see in the flex of the 2D materials, each bit of the flex, you can get a random response from each bit. And also I use quantum dots, which is colloidal quantum dots. So it is a tiny semiconductor particles between 2 to 10 nanometer. And it's very nice materials because you can see the different colors coming under different excitation just by changing the particle size of these materials. So to build a strong buff, we have to actually create a large number of CRBS, which means based on randomness, imperfections, impossible to replicate, unpredictable, and we also look into nonlinear response, and finally can be easy measure and has high emission responses. That's why I selected these nanoparticles, colloidal quantum dots. So the aim and the objective of my research is to build optical signature or fingerprint with these quantum dots, ensure the signature is unclonable and stable, build a high power efficient IA model for actually building edge IA, and integrate into our mobile wearable device and so on. There is a lot of challenges in this research, which I'm going to focus just on the top two here, which is actually how to ensure this is quantum tax is stable over time. Especially these are nanomaterials. It can be easy react with the environment, and it can be easy decay, the emission decay from these quantum dots. So we're going to study the aging properties of these nanomaterials, and we're going to find the good matrix of these materials to ensure the reproducibility and to ensure the unpredictability. There is so many other challenges, which means like, for example, most things is quantum, so we need to have error correction, and we need also to build a tiny AI for edge device, which means like we can use our phone to identify the object. So for aging properties, you can see on the top left here, different quantum dots with different matrix actually responds differently over days. So some of them are decays very quickly and some are a bit stable. So you can see on the bottom here, like in day 1, we can extract different features. However, day 14 and the pixels between the two, between days 1 and 14th is actually completely sometimes different. So this is actually, let's say, kill our application. So we would like to make sure these can be controlled. So we're going to build autoencoder variation model, which we can predict the decay rates over a number of years. And this could help us to actually build and generate a new data, and which means we can get a new materials as well. It's also can use for encode new images, and we can use also the autoencoder to actually feature extraction from these quantum dots. Okay, thank you. Sorry, I have 3 minutes only.
I should have said as well, we'll do questions for the seed funding at the end of this session. So now I'd like to welcome to the stage Dr. Ankit Dixit from the University of Glasgow, from the group of Beaulieu, I believe, so introduce their work. Thank you.
Thank you, Ben. And okay, so I'm Ankit Dixit. I'm currently working as a research associate with Deep Nano Group in University of Glasgow. And the seed-funded project which I'm working is basically to enhance the performance of static random access memory under the influence of process-induced variability. So what does it mean? First of all SRAM cannot need much introduction. It's very important and very critical component of any electronics hardware because of its properties, like it don't need a refreshing circuit unlike the DRAM. And the main if you talk about it with the industry perspective, industry wants a high density memory cell, and the performance of any memory cell or any SRAM cell could not be degraded with respect to time. So my work basically focus on how the different fabrication aspect can affect the reliability of the SRAM cell. So here you see it's a 6 transistor SRAM cell we have chosen because of this simplicity, so that we can implement our machine learning algorithm with that. And it's basically a cross-coupled 2 inverter circuit, and this is a 3-dimensional structure which we trying to implement in a TCAD simulator. And what about the stability means, like if you see this graph, I specifically choose only one variability here, the work function variability in a fabrication aspect, and you see for the same parameter of the device, even we have some deviation in this butterfly curve. So the main objective of the project to introduce a machine learning based model so that we can reduce the effect of process variability and as well as the device geometrical like the gate length and the fin and channel doping also. Another objective of this project is to enhance the performance of this SRAM cell so that we can have reduced leakage current, high increased drive current, and which can also boost up the speed and the lower efficiency. The final objective is to how we can reduce the simulation time, because currently if we have to simulate this 6 transistor cell in the mixed mode simulation of the TCAD, it will take a very long time. So these are the objective of this project. The methodology we are using, we are focusing on a single cell of SRAM, which is basically a CMOS inverter. So in a CMOS inverter, we have certain parameter or the device parameter, you can say like the gate length, fin height, channel doping, area factor, and these individual parameters significantly affect the performance of overall SRAM cell. So how we are trying to implement this project, we are trying to develop a machine learning based algorithm so that without doing a much large number of simulation before, so with a limited number of simulation, our algorithm will tell you that what will be the precise or what will be the best optimized parameter for the best output. For in this case, I have just considered the VTC curve of the inverter, and so that I can derive this static noise margin of the SRAM cell. The primary result we have obtained till now, like here you see, these are some certain number of parameters I have used, and for the whole, both the state like hold state and read state, I calculate the static noise margin is 0.36 and 0.19 respectively. But after the optimization, after implementing this algorithm with our TCAD simulator, we have significantly improved the result. It's approximately 20 to 25% improvement we are getting in both the hold state and the read state. And also the one thing is to note, like I just considered 3 parameters here. So within the 3 parameters, we have a good initial results. So the future optimization we are looking to increase these number of parameters, because as you increase the number of parameters, your algorithm will become a bit more complex and it will take more time. We also want to extend this work to the 3-dimensional of design, and again to better optimize our algorithm to speed up the optimization process. So these are the future optimization thing. Thank you so much.
Wonderful. Thank you, Ankit. Now I'd like to welcome to the stage our final seed funding speaker for today, or for this session, which is Dr. Natale Pruiti. I think I'm pronouncing that correct. Yes. Great, who's joining us from Glasgow. Thank you very much.
Thank you very much for the introduction. So, hello. Yes, we are the Photonics people, but you'll see that what we are trying to do is quite relevant for inverse design in general. Basically, we're just trying to use AI to help us with the design of integrated waveguides and devices in general that can be used for nonlinear photonics. Just to give you a bit of perspective, an integrated waveguide or an integrated device is a key component that's needed for on-chip generation of ultra-broadband optical signals that are coherent. And we're talking about several hundreds of terahertz of bandwidth here. And the importance of these signals is that, so they come in different shapes. One of these is the so-called frequency comb. And you can use these signals to act as a conversion gear between the optical and the RF domain, so that then we can access the optical stability through electrical systems. So this finds application in many different areas, such as sensing, metrology, and of particular relevance nowadays, quantum technologies. The tricky part here is that if we want to have a general arbitrary output signal, arbitrarily located across the optical spectrum, the integrated device is quite difficult to design because the space parameter is quite big. So for instance, we start with the material involved, but also the physical dimensions. So for instance, the cross-sections of our waveguides. But it's not limited to this, because we could have also a non-uniform cross-section along the waveguide path, as well as the presence of resonating structure, which is needed for these nonlinear devices. So you can see that the parameter space just blows up quite fast. So what we want to do is to feed all this information, so like the possible input signal, the desired output signal, and all the information we have on possible materials and cross-section dimensions, to a generative network that can actually help us to obtain a suitable design for our integrated nonlinear device. So this is our goal, but this is not the only way we plan to use neural networks, because the amount of data we need to train this generative network is quite large, and that can be quite time-consuming and also computational demanding. So in order to get some help with that, we're also going to use forward neural networks to generate this data. So what we've already been doing with simple wave structures, like simple cross-section, is to use a forward neural network to generate all the data for the optical modes. And this data is now being used along with more information on the waveguide structure, such as the non-uniformity of the cross-section across the waveguide path, and presence of resonant cavities and possible input signals, is going to be used with the physically informed neural networks based on nonlinear equations to generate all the sets of possible output signal, so that then we can combine all this information to the generative network that I've shown earlier. So yeah, that would be me. Thank you.
Wonderful. Thank you so much, Natalie. So the floor is open for questions to the seed fundings. So I think I'll start at the top there. Naima, do you have any concerns about current devices that implement physically unclonable functions?
Yeah, I mean, there is a lot of limitation still actually to make it as a real device, especially for buff systems. So matching the challenge and responses itself is a key point. Also, like what we're doing now, we actually just generate the data from the lab, which we use spectrometer. But however, once we move to a practical application, we still have a lot of challenges to do.
Great. I will come back to another question for Naima in a sec. Ankit, how are you using AI, or in fact everyone maybe in one sentence, how are you using AI to accelerate your research?
In one sentence, if I have to say, it speed up the optimization process. If I have to do the same thing in a conventional way, it takes so long time. But now with the AI, I mean, we know what is the optimized parameter for the particular circuit, and it speed up my initial guess, basically.
Great. Natalie?
Well, I already mentioned during the presentation, so it's really just about exploiting the fact that, so the problem is the parameter space is so huge that doing the design by hand just requires an insane amount of time. So the hope is that with the generative network, we can just reduce this design time and also maybe spark some new ideas, like things you wouldn't think about, materials that you could combine together that you haven't think about.
Great, thank you. And Naima, do you want to?
Oh, mine. Okay. Yeah, I mean, the cost of quantum dots itself, colloidal ones, is very, very cheap. Like we can synthesize it in our lab, and you can make a liter of quantum dots actually. And once we just mix with a different polymer, capping polymer, you can spread across a big sheet, just cut it in small pieces, you will get 1,000 of samples from just one sheet of quantum dots. So the cost is very cheap, that's why I select quantum dots, and it's practical. 2D materials is really hard because it's not easy to get a large area of 2D materials, so we just focus on quantum dots here.
Great, thank you. Natalie, do you want to have a go at how is your GAN trained?
Yeah, so we are not at that stage, so that's the ultimate goal. So right now what we're doing is using the forward neural network to actually generate all the data that is going to be needed to train the generative network. And for now we just use the basic training of reinforced learning, sorry, yes. And it's not clear yet, to me at least, because I'm going to come clear on this. I'm not the neural network person of the team. But so I don't know yet how we're going to do the training of the generative network.
Great, thank you very much. I think just in the interest of time here, we have lunch pretty soon, so I don't want to keep you from that. But there's some really interesting questions popping up here, so I really encourage people to approach our 3 seed funding recipients. And I'd like to thank them again for making the journey down or up. And yeah, that closes this module. Thank you very much. And so now I'd like to welcome again Atish to the stage, just to give an overall summary of the session and to give some closing remarks. Thank you.
Thank you all. As we're coming to the end of the session, just wanted to point out, you would have observed that time was a bit limited, but there were many interesting questions from everyone. So I'll just try to summarize all the talk that we've done so far. I will try to connect faces with the projects that they presented. And then if you have any questions that hasn't been answered, you can get in touch with the person. So the session was, you can see there were like 4 sort of presentations that happened. First one was from the researchers who are working with April, the interns projects, some seed funding projects that were just presented in the last one, and one industry collaborative project. So the researchers, we are being led by 4 professors here on the top right corner. Marlene, Jackie, and Bipin is here, so feel free to get in touch with them if you would like to have an idea of which direction we are going as far as materials discovery and device design is concerned in April. The researchers are listed here. Please feel free to get in touch with them as well if you are interested in a specific topic that they presented. The later session was about interns. Isa's presentation about the thermal property prediction. Jamie's presentation was about generative material models, and Zofia's about uncertainty quantification. So, and this was all overrun by researchers in the April. Finally, we have, so as far as this session is concerned, there are around 8 seed funding projects which are being run at the moment and which are from these 5 universities. Nima, Natalie, and Ankit just presented their work right now. There were many questions I could see, and I'm sorry we couldn't accommodate the time, so please feel free to get in touch with them during the lunchtime. And finally, last but not least, our industry collaborative work, which was done, possible because of Katrina Netti, who's the industry engagement, who looks at this side. The question was asked about intellectual property, and her help was very helpful in that process. Mohanad's work on AI-driven correction of TCAD simulations was the part of this talk. Finally, coming towards the end of it, I would just like to discuss where we would like to go forward. One thing that you may have observed throughout the session, we try to address different people doing different projects on different criteria from materials exploration to device optimization, and we are planning to go towards more of an integrative approach to solve this. EMOS was one such attempt, but in future we would like to see more things like that. As far as data is concerned, when it comes to material side, there is a huge, and I'm pretty sure you have observed this as well, huge amount of data available for materials, but when it comes to device, the data is quite sparse. Chandraban is working on this project. If one of you is interested in this sort of thing, we will be working on this as well in future. With the success with the project with STElectronics, we would like to, now since this is just the first year of April, in future we would like to have more of such projects which will directly get us involved with industry as far as research is concerned. And finally, we would like to make sure that the tools we build also follow the guidelines of a trustworthy AI tools. It's an important topic. Even DCIT just released their AI for Science guidelines recently, and we would like to keep our research in line with those. With that, I would like to thank you all thank you all the presenters and all the audience, and then now we will leave for lunch. See you soon. Thank you.